All right, we want to look at more on functions and their graphs. And we want to talk about when a function is increasing on an open interval. And the open interval is called I. That happens if f of x1 is less than f of x2 whenever x1 is less than x2 for any x1 and x2 in the interval. So this will be a place where the graph is going uphill. The function is decreasing on an open interval I if f of x1 is greater than f of x2 whenever x1 is less than x2 for any x1 and x2 in the interval. So the graph will be going downhill on an interval of decrease. A function is constant on an open interval I if f of x1 equals f of x2 for any x1 and x2 in the interval. So let's look at this graph and let's give the intervals of increase and decrease. Remember, an interval of increase is where, as you move from left to right, where the graph is going uphill. So notice from negative infinity to negative 1, and technically this graph actually is increasing indefinitely on the left end and the right end. So from negative infinity to negative 1, the function increases. We see that if we were moving from left to right, we're going uphill there. An interval of decrease is where the function is going downhill as we move from left to right. So one interval of increase is from negative infinity to negative 1. Another interval of increase is from 1 to infinity. So notice from x equal 1 and above, or values of x from x equal 1 and values bigger, the function is going uphill. Now the interval of decrease, as I move from left to right, the function has a downhill appearance on the interval between negative 1 and 1. Intervals of increase and decrease are always open intervals. They do not include the endpoints. Here's another graph. Let's look at the intervals of increase and decrease for this function, whose graph we see. The function goes downhill, indefinitely coming in from the left to negative 8. Additionally, from negative 2 to 0, and also from 2 to 5. That's when I have the intervals of decrease. In my math lab, it may ask you to separate these intervals with commas. Here, this is another way that they also may be given, and that is to talk about where the function is increasing and unite the intervals if there's more than one. All right, the intervals of increase are from negative 8 to negative 5. I'm sorry, to negative 2. Negative 8 to negative 2. And notice the graph goes uphill. When we give the intervals of increase and decrease, we give the x values. And so from x equal negative 8 to x equal negative 2, we see the graph goes uphill. From x equals 0 to x equal 2, as we move from left to right, the graph goes uphill. And from x equal 5, indefinitely beyond that, the graph goes upwards. When we want to define relative maximum and minimums, we're actually saying that the function f of a has a relative max if f of x is smaller than or equal to f of a for all x not equal to a in the open interval. We say that a function has a relative minimum if there's a b such that f of x is greater than or equal to f of b for all x not equal to b in the open interval. And so relative maximum is going to be a high point in a region of the graph, and the relative minimum is going to be a low point. So notice f of negative 1 is a relative maximum. F of 1 is a relative minimum. So f of negative 1, and notice it's the y value that is the maximum or the minimum. So the function value gives the y value. All right, here I have a relative minimum of negative 4. Notice that when x is negative 4, I have a lowest point in a region. And also when x is equal to 0. But notice even though 0, 0 and 5, 0 are low points, it's the y value that's the relative minimum. So it's really just one relative minimum, and that's 0, even though it happens for two different x values. 6 and 10 are y values that are relative maxima. So if there were only one, we would say maximum. Maxima is the plural. And again, note that y values are the actual minimum or maximums. X's tell us where those occur, but the actual maximum or minimum is a y. A function is an even function if f of x equals f of negative x for all x in the function's domain. And the function is an odd function if f of negative x equals negative f of x for all x in the function's domain. So this actually, both of these are types of symmetry. So an even function, remember, has f of negative x equal f of x and is symmetric with respect to the y-axis. An odd function, where f of negative x equals negative f of x, is symmetric with respect to the origin. So when we look at the graph of A, that's an even function. We have y-axis symmetry there. When we look at B, we have an odd function. We have origin symmetry. And in an odd function, whatever you see in quadrant 1, you see the mirror image in quadrant 3. Whatever you see in quadrant 2, you see the mirror image in quadrant 4. C is neither, and D is even. So D, we have y-axis symmetry. C, we have no symmetry at all. So when we are given a function in function notation, to see if it's even or odd, we replace x with negative x. And in this problem E, we see that f of x actually is the same as f of negative x. So f of x is even. When you raise negative x to a fourth power, you get x to the fourth. When you raise negative x to the second power, you get x squared. Now when we do f, g of negative x turns into negative 2x cubed minus x squared. That's not equal to g of x, and g of negative x is also not equal. So if the fact that g of negative x doesn't equal g of x means it's not even. The fact that g of x, negative x doesn't equal negative g of x means it's not odd. So let's look at h of x. If I replace x with negative x, I get negative x over the square of negative x minus 1, which simplifies into negative x over x squared minus 1. Whenever you raise negative x to an even power, you just get x to that even power. And I can bring that negative sign down level with the fraction bar, and this is equal to negative h of x. So in f, in e, the function was even. In f, we had neither an even nor an odd function. In G, we have an odd function. Now we want to look at piecewise functions. These are functions defined by two or more equations over a specified domain. And here we're given a piecewise function. If x is less than 0, f of x is x squared. If x is greater than 0, f of x is 1 over x. When x equals 0, f of x is, again, x squared. So when I replace x with negative 2, I square that because that's an x that's less than 0. So y is 4. When x is 0, I square 0 because that value is where I use x squared. And so as I go to graph this, I have an arrow indefinitely to the left that's going up. On the part of the parabola y equal x squared, and that ends when x is 0 with a solid dot. Then I have the graph of one branch of y equal 1 over x, the branch that's in the first quadrant for x bigger than 0. And it's kind of hard to draw that with on my tablet here. I just don't have the control I need, so I'll give you a more precisely sketched graph. And that's what that would look like. And I have a solid circle at 0, 0. Because x squared is 0 when x is 0. So this is officially what the graph would look like. So this is a much clearer picture. It doesn't look like an L. It is a smooth curve. It doesn't have a sharp corner. It was hard for me to draw that mechanically. Now let's look at this function, which is x squared if x is less than 0. It's equal to 2 if x equals 0. And it's equal to the square root of x if x is greater than 0. So f of negative 2 is the square of negative 2, which is 4. F of 0 is 2. And f of 2 is the square root of 2, which is approximately 1.4. So we're going to graph that in. And notice that I have an open circle at the origin because x squared is 0 at the origin, and so is the square root of x. That's not a point on the graph. Here, I'm given the function, and I want to give the rule. So notice I have the absolute value of x for any value of x that's less than 1. Now to find the equation of this line segment, I need to first find the slope by using these 2 points on the line segment, 1, 0, and 4, negative 3. So I'm going to use the formula for finding slope when I know 2 of the points. So slope is often referred to as m. That's the difference of the y values over the difference of the corresponding x values. So here I get 3 over negative 3, which equals negative 1. Now I'm going to use the point slope equation, which is y minus y1 equals m times x minus x1. And I can use either of these points. I'm going to use the point 1, 0. So y minus 0 is the slope, negative 1 times x minus 1. And notice when I simplified that, y was equal to negative x plus 1. So that's the function that's used when my x's are between 1 and 4, including 1 and 4. So that's how I would define that piecewise function. Now when I look at this graph, I look at these points on the left branch, and I realize whatever x is, y is its reciprocal. So this is the part of the branch of the function y equals 1 over x. Because I see you're getting that y by taking the reciprocal of x. And that's only my function if x is less than or equal to negative 1/2. So notice this includes negative 1/2 because of the solid dot. Then I look at the other branch and I see whatever x is, y is the square root of x. And that is my function for x's between 0 and 4, including 0, and not including x equal to 4.